The relative permittivity of a material is its dielectric permittivity expressed as a ratio relative to the permittivity of vacuum. Permittivity is a material property that expresses the force between two-point charges in the material. Relative permittivity is the factor by which the electric field between the charges is decreased or increased relative to vacuum. Likewise, relative permittivity is the ratio of the capacitance of a capacitor using that material as a dielectric, compared to a similar capacitor that has vacuum as its dielectric. Relative permittivity is also commonly known as dielectric constant, a term deprecated in physics and engineering. Definition: relative permittivity is typically denoted as I micron R, I per mil and is defined as where I micron, I per mil is the complex frequency-dependent absolute permittivity of the material, and I micron 0 is the vacuum permittivity. Relative permittivity is a dimensionless number that is in general complex-valued. Its real and imaginary parts are denoted as. The relative permittivity of a medium is related to its electric susceptibility, i.e., as I micron R, I per mil equals 1 plus IE. In anisotropic media the relative permittivity is a second-rank tensor. The relative permittivity of a material for a frequency of 0 is known as its static relative permittivity. Terminology: this historical term for the relative permittivity is dielectric constant. It is still commonly used, but has been deprecated by standards organizations, because of its ambiguity, as some older authors used it for the absolute permittivity a micron. The permittivity may be quoted either as a static property or as a frequency-dependent variant. It has also been used to refer to only the real component I micron or of the complex-valued relative permittivity. Physics: in physics, permittivity is a complex quantity. The imaginary part corresponds to a phase shift of the polarization P relative to E and leads to the attenuation of electromagnetic waves passing through the medium. By definition, the linear relative permittivity of vacuum is equal to 1, that is a micro equals a I micron 0, although there are theoretical nonlinear quantum effects in vacuum that exist at high field strengths. Measurement: the relative static permittivity, I micron R, can be measured for static electric fields as follows. First, the capacitance of a test capacitor, CO, is measured with vacuum between its plates. Then, using the same capacitor and distance between its plates, the capacitance Cx with the dielectric between the plates is measured. The relative dielectric constant can be then calculated as. For time-variant electromagnetic fields, this quantity becomes frequency-dependent. An indirect technique to calculate I micron R is conversion of radio frequency S-parameter measurement results. A description of frequently used S-parameter conversions for determination of the frequency-dependent I micron R of dielectrics can be found in this bibliographic source. Alternatively, resonance-based effects may be employed at fixed frequencies. Applications: energy. The dielectric constant is an essential piece of information when designing capacitors, and in other circumstances where a material might be expected to introduce capacitance into a circuit. If a material with a high dielectric constant is placed in an electric field, the magnitude of that field will be measurably reduced within the volume of the dielectric. This fact is commonly used to increase the capacitance of a particular capacitor design. The layers beneath etched conductors in printed circuit boards also act as dielectrics. Communication: dielectrics are used in RF transmission lines. In a coaxial cable, polyethylene can be used between the center conductor and outside shield. It can also be placed inside waveguides to form filters. Optical fibers are examples of dielectric waveguides. They consist of dielectric materials that are purposely doped with impurities so as to control the precise value of I micron R within the cross-section. This controls the refractive index of the material and therefore also the optical modes of transmission. However, in these cases it is technically the relative permittivity that matters, as they are not operated in the electrostatic limit. Environment: the relative permittivity of air changes with temperature, humidity, and barometric pressure. Sensors can be constructed to detect changes in capacitance caused by changes in the relative permittivity. Most of this change is due to effects of temperature and humidity, as the barometric pressure is fairly stable. Using the capacitance change, along with the measured temperature, the relative humidity can be obtained using engineering formulas. Chemistry. The relative static permittivity of a solvent is a relative measure of its chemical polarity. For example, water is very polar, and has a dielectric constant of 80.10 at 20 AA degrees Celsius, while hexane is nonpolar, and has a dielectric constant of 1.89 at 20 AA degrees Celsius. This information is important when designing separation, sample preparation and chromatography techniques in analytical chemistry. The correlation should, however, be treated with caution. For instance, dichloromethane has a value of I micron of 9.08 and is rather poorly soluble in water. At the same time, tetrahydrofuran has its I micron equals 7.52 at 22 AA degrees Celsius, but it is completely miscible with water. This is even more apparent when considering the I micron of acetic acid and that of iodothane. The large numerical value of I micron is not surprising in the second case, as the iodine atom is easily polarizable. Nevertheless, this does not imply that it is polar too. Lossy medium, again, similar as for absolute permittivity. Relative permittivity for lossy materials can be formulated as, in terms of a dielectric conductivity I florin, which sums over all the dissipative effects of the material. It may represent an actual, electrical conductivity caused by migrating charge carriers, and it may also refer to an energy loss associated with the dispersion of I micron, the real valued permittivity. Expanding the angular frequency I per mel equals 2 I euro Ci, and the electric constant I micron 0 equals 1 / a micron 0 C2, it reduces to. Whereas the wavelength, c is the speed of light in vacuum, and I equals a micron 0 c/2 I euro a per mil 60.0 ZA1 is a newly introduced constant. Metals, permittivity is typically associated with dielectric materials, however metals are described as having an effective permittivity, with real relative permittivity equal to 1. In the low-frequency region, which extends from radio frequencies to the far infrared and terahertz region, the plasma frequency of the electron gas is much greater than the electromagnetic propagation frequency, so the complex index N of a metal is practically a purely imaginary number. Expressed in terms of effective relative permittivity, it has a low imaginary value and a negative real value. See also. References